Yeah, so Steve Ellingson here. I am a electrical engineering professor at Virginia Tech who spends a big chunk of his time doing radio astronomy. When I do radio astronomy, it's typically instrumentation or data processing techniques. Those techniques are typically, are often interference related, so certainly a relevant audience here. Then occasionally I get to do science. For two reasons. One is because sometimes you just come across things which are too interesting not to look into, and the other reason would be it's hard to do this kind of work without knowing something about the science. So I'm going to try to give you just enough science so that you can kind of see the technical aspects, and hopefully this won't turn into a course on astronomy, but we'll see. Let me begin with what we're talking about here, the radio telescopes. So an easy way to bound the discussion here is to limit ourselves to radio telescopes in North America, which I figured was okay, since we're talking about this National Radio Dynamic Zone project. But be aware that at least here, I'm limiting myself to scopes in North America. And of course, there are the iconic ones, the Green Bank Telescope and the Very Large Array. Very Large Array, by the way, also goes by names of EVLA and JVLA. I assure you, they are the same telescope. Traditionally here, you put two big images, one image each of one of these telescopes, and I resisted the temptation to do that because it gives the wrong impression. It gives the impression that those are the only telescopes that matter, or in North America. Certainly not the case. Active, but important and less well known. I've just tried to include the ones I could quickly think of. ARO in Arizona, CHIME in British Columbia, EHT, which overlaps North America, Hat Creek, California, there's several. Haystack in Massachusetts, there are several. The LMT in New Mexico, in the original Mexico. LWA in New Mexico. Owens Valley, there are several. There's millimeter array in Mauna Kea, VLBA, which is several sites all over the continental United States and beyond. And the list keeps going, and I'm certain I've forgotten somebody. So whoever sees this and is upset because I forgot their telescope, it's just my incompetence. That's not important. And then there are experiments, innumerable special purpose instruments, temporary instruments, pathfinders, which is in our business somewhat of a synonym for a prototype, but it has a different connotation. It's more than a prototype, and others doing important work. So you may be closer to a radio telescope than you think, and there's a lot more going out here than I can directly address. But I just want to give you a feeling for the fact that this is there are many such things around. Of course, on the horizon, I should say that there are telescopes coming up. And this is, of course, relevant if you are planning for the future and you want to kind of see how the situation might change, how the landscape of instrumentation might change. It would be important to consider the next generation VLA. That's not certain to happen, but it's come quite a long way. So it looks like something like that's going to happen. I've got a slide on that. The Deep Synoptic Array is another instrument which is quite likely to become quite large. Not certain to happen, but I don't have a slide on that, but I guess I could talk about it later. And then, of course, you realize there's one iconic telescope missing up here. That would be Arecibo. Most of you know Arecibo suffered a catastrophic collapse some months ago. And there's talk about rebuilding it in some form. That's too early to really consider here. So what does this talk about? The request of me was to do a talk about how radio astronomy receivers work, why they're so sensitive, why they need such a great deal of protection. I think I can address those. The answer will involve some of the following things, which I'll address in my slides. The instrumentation itself, how radio astronomy gets done, that is the techniques which impact sensitivity. What we even mean by sensitivity. This is a conversation which is, in my experience, obvious and slippery, because sensitivity can be defined in a whole bunch of different ways. And I'll be scrupulous to be sure that you know what I'm talking about here, hopefully. Observing modes, you will find there are many. I find most people who are not of radio astronomy don't realize this. There are many, many ways telescopes get used. It is not simply pointing a big dish at a point in the sky and seeing how much power you get. Utilization of the time frequency plane. This, of course, is relevant to this audience, so I thought I'd put it in there. Then vulnerabilities and countermeasures. So this is the interference stuff. I will say something about how interference shows up. I'll say something about its impact. I'll try to say something about its mitigation. But being somewhat of an enthusiast in this area, I find that I'm going to have to harshly curtail my discussion of that, or this will run out of the allocated time. But I will certainly make myself available for subsequent discussion. So being a teacher, among other things, always important to emphasize what it is that people should walk away with, students should walk away with. And the idea here is that once you get through this, you should know enough to do some basic but meaningful analysis of sensitivity and the vulnerability of radio telescopes. So this is what I endeavor to do. Here I've attempted to left justify my slides. So the organization is not really the traditional one. What I've tried to do here is organize it so that as people have to drop off, or if we run out of time, the most important stuff should have already appeared, and we'll get to more details later. So hopefully that organization is not disorienting, but I think you'll enjoy it. I should say what this talk is not going to be about, just so nobody's waiting for something that's not going to come. I'm not going to talk about spectrum policy. I'm not going to talk about regulation. I'm not going to talk about enforcement. I'm not going to talk about the value to society. I'm not going to talk about economic considerations. I'm not going to talk about the science explicitly, although I can't avoid saying a few things. I'm not going to talk about scientific accomplishments. Those are all things that are of immense importance, to be sure, especially to this audience. But I think here what you want is to know some tech, and that's what I'm going to try to do here. So I will work mightily to avoid veering into any of these topics. Again, not because they're not important, but just because we want to talk about tech. I should also say it's traditional in these things to say something about the history of radio astronomy, which is fascinating. But again, I don't want to do that. I want to focus on the tech. But I do have to say one thing, kind of as a motivational issue. Radio astronomy is unique among the astronomical disciplines because it was literally invented by radio engineers. The first radio astronomer was an electrical engineer. Many radio astronomers have been electrical engineers, and there's a bidirectional flow of expertise that's had a huge impact on radio astronomy and then subsequently back on radio engineering in general. And I think any competent wireless engineer can learn the essential concepts. You shouldn't be intimidated by any of this. So much of it's just lingo and kind of recalibrating your way of thinking about the concepts you probably already understand. So I would encourage you to not be intimidated by anything I'm going to show here.